Welcome back, and we want to look at example 4.2.3. I'm going to take W to be the plane x plus y minus z equals 0 in R3, and I'm going to use the regular dot product in R3, and I want to look at projections. All right, if you remember what the formula for projection tells you, you need to have a orthogonal basis for W, and then it's just a matter of applying dot products. So I need an orthogonal basis for W. All right, so W is a plane. It has normal vector 1, 1, minus 1, and this plane is x plus y minus z equals 0. What I'm going to do, we'll see in the next section how to construct an orthogonal basis, but now since we don't have anything, I'm going to use geometry. I'm going to start with any vector that's perpendicular to n, so any vector along the plane. So here, this is n, so I can take 1, 0, 1. And now I want a second vector. That vector needs to be perpendicular to n so that it is on the plane. It needs to be perpendicular to v1 because I want an orthogonal basis. So what I'm going to do, I'm going to take v2 to be, I'm going to take n cross v1. Remember the cross product, right? So that's 1, 1 minus 1 cross with 1, 0, 1. You can compute it using whatever notation you are used to. I like this one, so I'm going to take this, and this. I'm going to use minus 1 plus 0. I have minus 1, and I have minus 1. Wait. Oh no, minus 1, that's minus 2, sorry. All right, so my basis for W, wait, let me recompute all of these. I don't know what I did. All right, so first one is this one. I get 1 minus 0, I get 1. Second one is this one. I get minus 1, I get minus 2. So minus 1, I get minus 2. And the third one is this one. I get 0, minus 1. I get minus 1, minus 1. All right, so my basis for W is 1, 0, 1, and 1 minus 2 minus 1. It is orthogonal. Perfect. I want to find an orthogonal basis for W perp. All right, like we said before, geometry is really helpful here. Here's W perp. I can take n. Notice that for a 1D object, orthogonal bases are quite simply basis, and that's part of the reason projection onto one vector was easy. That's like projection onto a line. You didn't need to worry about your basis being orthogonal. All right, compute the projection on W and the projection on W perp of this element 3, 4, 1. All right, projection on W of U. All right, so that will be U dot my first vector. So this, I'm going to use it as V1, V2, and let me call this one, let's just call it N, since that's what we had before. So U dot V1, 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 V1. And then U V2, 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 V2. All right, U is 3, 4, 1, V1 is that. So I'm going to get 3 plus 1. V1, V1, that's 1 plus 1. I get this times V1 plus, and then V2 times u, that's 3 minus 8 minus 1. V2 is 1 plus 4 plus 1. And so I'm getting, I want to save a bit of room, so I'm going to use horizontal vector. This is 2. This is 6 minus 1. All right, so I get 2 times the first, so that's 2, 0, 2, minus 1 minus 2 minus 1. I get 1, I get 2, and I get 3. Vector 1, 2, 3. That looks made up. All right, let's try the projection onto the perpendicular subspace. So I get u dot n, 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 all of this times n. So u dot n is 3 plus 4 minus 1. This is n, this is u. And then n dot n is 1 plus 1 plus 1 times n. So I get 6 divided by 3, I get 2 times n. So I get 2, 2 minus 2. All right, so let's check. What happens if I take the projection onto W plus the projection onto W? That's like taking X plus W right here. So I should be getting U back. All right, so that's 1, 2, 3 plus 2, 2 minus 2. I get 3, 4, 1. I get U. So we did well. All right, so one thing, let me shrink this a tiny bit just to make sure what I write next is clear. All right, so theorem 4.2.5, let U be any element of an inner product space V, let W be any subspace of V. Projection of W into U is the element of W closest to U. So this shouldn't be here. So we'll prove this on an assignment or a worksheet. Here's the picture. This is U. That's the element. This is the projection. That minimizes this distance. All right, so again, since the distance depends on the inner product, so does the projection, so does the element that minimizes it. So, and that's part of the reason our projection here uses the dot product so heavily.